All right. I'll get started. Let me begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, I thank you for this class, for these students. Just ask you just guide our steps today, Lord. Help us to glorify you what we do. And we just thank you again, Lord, for your many blessings. In your name I pray, Lord Jesus. Amen. I will put that away. Let me pass around the real attendance sheet here. Somebody, let's see, what was, I think the last date on here was the 30th. I think it's is it the 1st today? Okay. Let me steal your pencil momentarily.
Oh. I was pulling out a pencil. If you want to put it in pen, someone change the date.
Yeah, I know. If anybody, you guys can, if you guys feel the need, don't change the date, but if you did, I mean, what could I do? All right, so I want to talk about factoring and solving with quadratic polynomials. Now, one of the fundamental confusions in this class that I try to combat. In every semester I lose this war, but I keep fighting. Is that there is a difference between solving an equation and factoring. Factoring is, well, factoring. The answer with factoring is an expression, right? If you solve an equation, on the other hand, what are you looking for? You're looking for like a set of answers, right? Either a pair of numbers, a number, a statement that there is no number that solves it, right? Watch out. Or for a almost. Or for an inequality, an interval is the solution. I should have warned you. Sorry. Where was I?
That's all right.
Okay, good. So like, for example, 1. If we were to look at, I don't know, x squared minus 16, all right? And I said, factor this polynomial completely over the reals. That would look like the following. That would just look like, this is x squared minus 4 squared, right? And I remember my pattern. Let's write this at the top. A squared minus b squared, right? Difference of squares. A plus b times a minus b. We're going to use that today a lot, all right? So x squared minus 4 squared. Now I think of that as the difference of squares, and I apply my difference of squares formula, right? Which is that this is what? X plus 4 times x minus 4, and that's it. That is the factored form of this polynomial. If I give this thing a name, I could call this, say, p of x. All right, that's p of x. This is p of x factored completely over the real numbers. So this is my symbol for real numbers. If you think that's a hashtag, you're wrong. That is the pound symbol. There are no hashtags in this class, to be clear. You guys are so serious. All right, well, I guess I'll allow it. So inevitably, on the quiz or the test that comes up, I say factor. And what do people do for this problem? They tell me, x equals 4, x equals minus 4. And then I have to take the credit off because they haven't answered the question. I asked you to factor it. The answer for a factoring question is an expression, which is factored. That is it. We're not solving an equation. We are rearranging an expression by factoring. That's it. Yep.
Does the same go for a completing the square question?
Right, well, yeah, we're going to get to there. But completing the square has two uses. Completing the square can be used to factor, but completing the square can also be used to solve an equation. You can go either way. I teach completing the square as something you do to an expression because that, if you can do it to an expression, you can use it to solve an equation. But if you can only think of completing the square in terms of solving an equation, then you're at a loss when you try to do it to the expression. I'm not speaking hypothetically. I've met students in previous terms who have been stuck because they have this only think about completing the square in terms of an equation viewpoint. It's not a good viewpoint. Oh, anyway, factor. Now, what's the corresponding equation? What if I say solve x squared minus 16 equals to 0? Then what do? Well, we factor it, right? But then we do one more step, right? We say, aha, so that says either x equals to minus 4 or x equals to 4, right? Now, this is a different problem. Factoring and solving are different. The answer to a factoring problem should be an expression. It should be something with x. It shouldn't be set equal to 0. When you set something equal to 0, we're talking about an equation. Equations are different than expressions. All right? So, all right. Anyway, does that make sense? Now, we had another way to solve this last time, right? What did we do? We isolated the square and used the square root property. So any of these kind of problems, we can also use the square root property to solve, right? Also true. Let's do more factoring. We could definitely afford to do more. So example 3. What if you're up against 9x squared minus 17? Can you factor this? You guys try to factor that. And try to use difference of squares. What is 9x squared as a square? Square of what? Let's see here. I'll do the easy part. Something squared minus something squared. Now you guys just got to fill in the blank. What do I put in those? Surely somebody can tell me the first one. What do I put there? 3x. I heard a still small voice. I heard 3x. Very good. Yeah, 3x quantity squared. If I square that, I get back 9x squared, right? How about the other one? How do I get 17? What do I put in the parentheses? Root? Yeah, root 17. Yeah. So square root of 17 here, right? I'm now looking at the pattern a squared minus b squared. So, answer 3x plus the square root of 17 times 3x minus the square root of 17. There we go. Factored. Yes, sir. Has everyone been attended? Everyone been attended to? Anybody miss it? No? Got it. Thank you, thank you. Does this make sense? Okay. I mean, this one's obviously not as pretty as the other one, right? There it is. Okay, so example 4. What if we were up against, I don't know, let's say 3x plus 1 squared minus 2x plus 3 squared. Could we factor this? It is what? It is a difference of squares, right? So we can factor it. So we think of this as A, think of that as B. Basically, we just write down A plus B times A minus B, which works out to what here? 3x plus 1 plus 2x plus 3, parentheses, 3x plus 1 minus, and I would urge you put a parenthesis here to make sure you distribute this minus to the totality of the b term, all right, which is 2x plus 3. All right, then what? Then we should gather like terms, right? So we've got what? We've got a 5x plus 4 times what? Times x minus 2. Am I right? Now sometimes I want to factor a number out so that I only have x's in my factors. Do you guys know how to do that? So this would, they're already factored, right? But let me show you another algebra step that we can make, okay? So one additional algebra step we could make here would be to factor out a 9. All right, and 9 of course is what? 3 times 3. See, I can factor a 3 out of this. And what do I have to do to be fair? Well, I could put 1/3 square root of 17. Oh, my bad. No, it's fine. And then this would be x minus 1/3 square root of 17. That was kind of a tricky one. Let me do an easier one. How about here? I can factor the 5 out. How do I factor 5 out? Let me show you. Let me do the steps here. This is 5x, right? How do I make a 5 appear on the 4? What you do is you multiply and divide by 5. That's multiplying by 1, right? So this is like 5 times 4/5. Once I do that, I have a common 5 that I can factor out, right? So this is 5 times x plus 4/5 times x minus 2. Now, if I tell you to factor a polynomial, I do not expect you to do what I just did in the last two things, that factoring the number out, that's optional, all right? But there are places where it's helpful to know how to do that, all right? Any questions? Are we all good on difference of squares? If I ask you difference of squares, you're going to knock it out of the park? Yeah?
So can I go up front and review the process with you?
No, but I can talk to you in office hours. But
Dang it.
don't worry, we're about to do something more interesting. Yeah.
My question would be with difference of squares at the start of example 4, the minus sign between a and b, that just gets totally dropped. Is there any like mathematical principle behind that?
The principle is just that if we multiply this out, what
The
happens?
equivalent of
Right. I mean, if we FOIL this, yeah, we FOIL this out, we get a times, that's a squared minus ab plus ba minus b squared, right? So these guys cancel because they commute. Those numbers commute.
That makes sense.
And so it's just an identity.
Got it.
Mm-hmm. All right. So example 5. What if we have to factor x squared plus, I don't know, 8x minus 3? Okay, so my instruction in each one of my examples today is going to be factor, all right? We talked a lot about how to solve the equation last time. I'm focusing only on factoring for the rest of today, okay? We're just factoring. We're going to factor and factor and factor and factor and factor. We're going to be so tired of factoring by the end of this lecture that you'll be so bored with it. You're like, I'm already bored.
I will never get bored.
You'll never get bored? See, some people are already bored. So not you? That's good. I wouldn't recommend anything else. Let's see here. So we can't factor this, right? If you were to try to multiply this as what? Like, if you were to try to write x minus, x plus, let's say some number, a times x plus some number b, what would that look like? When you multiply that out, you get x squared plus, if you work it out, parentheses a plus b, x plus ab, right? So when you look at these two things, that means you need to be able to find a plus b equals to 8. And you also need to be able to find ab equals to minus 3. I wrote that out in words last class, right? But here's this argument I'm just showing you is called equating coefficients. Two polynomials are only equal if they have the same coefficients, right? So you can match the coefficients to factor. But you guys said that has no solution. That's partly true. It has no easy solution. It's got no integer solutions. I can't find whole numbers that make that work. So let me show you the way. So what we're going to do is complete the square. Completing the square is an algorithm. So here we go. We take 1/2 of 8, which is what? 4. We square that. To be fair, I have now added 16. So to be fair, I have to subtract 16. What I've written in blue is identically equal to what I underline in blue right above. The 3 rides along. All right, so that is, if I called this thing p of x, let's say, to give it a name, this is exactly p of x again. Right, those are equivalent expressions. Then what can I do? Let me just rewrite it a little bit neater. That is x plus 4, quantity squared, minus wait, I was about to say 29 because I'm an idiot. What is that? I think I'm getting sick, guys, so don't stand too close to me.
Just like me, for real.
Oh, yeah? Someday this umbilicus is going to be the death of me.
Let's hope not.
But it would make a good story, right? Yeah. Look, you guys, at least 2 of you already know what to do with a 19. What do? We change it to a square root of 9.
Square root of 19.
19 squared, right? The square root of 19 squared is equal to 19, right? Now what do we have? Difference of squares. So we can use the difference of squares pattern yet again. X plus 4 plus the square root of 19 times x plus 4 minus the square root of 19. Factored. Done. Did you notice something about that? Did you have to guess any numbers to factor? There's no guessing. It's an algorithm. All you have to do, if it's already in the form where there's just a leading coefficient of x squared, if you've already got an x squared, right? You simply take half of the coefficient of x, you group it in the square, you subtract the number to make it an identity, leave the other one alone, then you will get a difference of squares if it can be factored over the reals. All right? Now sometimes it's imaginary. That could happen. Like, well, let's look at another example here. Example 6. Let's try this one out. What if we had p of x equals to x squared plus 4x plus 4. let's try my trick. So we take x, we take 1/2 of 4, which is 2. We have x plus 2 squared. I'm supposed to subtract the square of what I put there, so I subtract 4. Again, those terms I just wrote down are identically equal to what I wrote in blue. The minus 4 is still there. I mean, the plus 4 is still there from the previous term. What just wait, what just happened? Well, this one's kind of funny, isn't it?
Yes, it is.
So here we didn't even have to use the difference of squares formula, right? Because this polynomial is just, it's just a repeated root, right? It's a repeated factor. It's x plus 2 squared. So when you do completing the square on this, it just directly factors the thing. Now, most of you, if I had written over here like this, right? And I put x here and I put x here, you guys would have got that that's x plus 2 times x plus 2. I'm not saying that you wouldn't have, right? But if you understand the completing the square algorithm and you execute it carefully with good arithmetic, you will find it. It's not if you will see it or not. It will happen. Like, it's there. You have to get it. Let me keep doing these. Aw, man. Did I leave my... oh, here it is. So, what if... Does every quadratic factor over the real numbers? So let's see here. Example, where am I? 7. So you guys try the thing we're just doing on x squared plus 4x plus 5. You guys try completing the square on this while I'm moving my camera. See what you get. The pattern's going to be different this time, a little bit. So what do we do? This is 4. What's half of 4? 2. I think I keep doing that again and again. I'll try to come up with some more variety here in the next example. So that's x plus 2 squared. And then I have to subtract the square of 2, which is 4. All right? Those two terms are these two terms. I still have my plus 5. Oh, see what happens? What do you got? Looks like we've got a plus what? Plus 1. So here's basically this is the remark I need to make for you. Remark. If completing the square produces pattern a squared plus b squared, then we cannot factor over the real numbers. So if the instructions are factor over the real number system, at this point, you're done. You're like, oh, well, we can't factor it because it's the sum of squares. Like anytime you see this pattern, this is a theorem for us. That means you're done. That quadratic cannot be factored over the reals. Okay?
Let me write down.
Yeah, go for it. Yes, sir.
Just for refreshing, when you're completing the square, the minus 4 there represents 2b squared because that's what you derived from the half.
B over 2.
Okay.
I'll try to, we'll keep working examples, so, yeah. So we can't factor over the reals, but what could we factor over? Imaginary. How can I change that 1 into a square? What is I squared equal to? I squared is what, Michael? You know.
So,
I squared is, remember?
-1.
-1. That's right. So what happens if I multiply this equation by -1? I get minus I squared is equal to 1. So complex numbers allow me to turn positive numbers into the square of an imaginary number with a minus. Eh? So this is actually x plus 2 squared minus I squared. And guess what? Difference of squares still makes sense for complex numbers. They have the same distributive properties of real numbers, and then we go back to our usual song and dance. This is x plus 2 plus I, x plus 2 minus I. So this is how, let me give this thing a name. I will call it Bob. Bob of x. So this is the Bob of x factored over the complex numbers. The interesting thing about complex numbers is that if you have a polynomial, if you have a quadratic, it always factors over the complex numbers. There's no quadratic which will not factor if we're allowed to use complex numbers. If we're only allowed to use real numbers, well, sometimes the quadratic can factor, sometimes it can't, right? Like this example 7, it cannot factor with real numbers, but it will with complex. Now, usually, so I ask 2 different kinds of questions on the upcoming test. Is like I'll ask one question, which is factor these polynomials completely over the reals. That question, when you get to something like this, you're like, oh, that's as far as it goes. It's, you know, it's atomic. You can't split it. Oh, wait a minute. That doesn't make sense anymore. It's like a quark. You know, you can't subdivide it. I don't know, whatever. Anyway, it's fundamental. You can't break it down further. However, another class of problems I might ask, I might say factor this quadratic over the complex number system. In that case, you always know that there's something to do, because it can always be factored over the complex number systems. And how do you factor a quadratic over the complex number systems? Without fail, complete the square. You can just complete the square. It always works. Questions? I should show you more examples, right? Yeah?
That's the complex number side, right?
Yeah, this is the set of this is the symbol for the complex numbers. Complex number system. This R is equal to minus infinity to infinity in your usual interval notation. All right. Let's do another, and let me make it. I'll make this one a little bit uglier, guys. Okay, I'm going to bring fractions into the mix. All right, because you notice that I've been judiciously. I've been careful to make the coefficient of the x even, so that when we divided by 2, it didn't hurt us. But it doesn't have to be that way, does it? So example 8. What if we were going to factor, oh, I don't know, x squared minus 3x plus 7? Let me make that a minus 7, because I'm not trying to make everything complex numbers. I think if I make that a plus 7, it will be a complex, only factor over the complexes. So I'm going to stick with a minus to make it more interesting. Let's complete the square. What do we do? We take x, now 3, we divide 3 by 2, so 3 halves. All right. Then what? What do we have to subtract to be fair, to keep, you know, to match the first 2 terms there? the square of that number. What's the square of, what do I have there? Minus 3/2? So the minus doesn't really matter, right? When you square minus 3/2, you just get what, 9/4? So we have to subtract 9/4 from this. So minus 9/4. That, again, will match those two terms. Is exactly equal to those two terms. I still have the minus 7. All right? Indeed. Now, it's a little bit trickier, right? But we can do this. We can convert that to a fraction. So we've got x minus 3/2, quantity squared. What do we have? What's 7 in terms of fourths? I heard a 28/4, I'll take it. So what is, and it's a minus 2, right? So what's minus 9 minus 28? What, in other words, what's 28 plus 9 is, I heard a 37. So minus 37 over 4. All right. Approved? Okay. So that, if you think about it for a second, or two, is minus the square root of 37 over 4 squared, right? So we can still do that. Of course, we could simplify this further, right? What's the square root of 37? What is the square root of 37 over 4? Well, that's equal to the square root of 37 divided by the square root of 4 by properties of the square root, right? Which is also known as square root of 37 over 2. So let me put that in the mix here before I do more. X minus 3/2 squared minus the square root of 37 divided by 2 quantity squared. By the way, just like mental exercise as we're doing this, think about this. If instead of having minus 7 in this problem, right, if I had a plus 7, we would have yes, we would have had 18, we would have had 28 minus 9 rather than, and it would have been positive, right? Which would have made this in a polynomial which does not factor over the reals. By the way, when they don't factor, they're either called prime or sometimes they're called irreducible. So these, just in terms of language, this right here, we have a name for it. It's either a prime or irreducible, which is just a fancy way of saying you can't factor it. All right? Can't break it up. Cannot be reduced. But this one, we can, right? Because we're back to difference of squares again. So what we got? X minus 3/2 plus the square root of 37 over 2, parentheses, x minus 3/2 minus the square root of 37 over 2. Factored. Yay. So, yes, when the coefficient of x is not even, it's annoying because then we have to deal with fractions, right? You know what would be even more annoying? If I made like a fraction here that had a different denominator, right? Then I'd have to make a common denominator. When might that happen to us? You're like, these problems are only easy because you keep making the leading coefficient 1. That is true. I have made the leading coefficient 1. If the leading coefficient's not 1, it becomes less pleasant. Let's look at that. Let me try to show you a path through the wilderness. How do we do this? 2x squared plus 3x plus 1. There, that's a relatively innocent looking polynomial. How do we factor that? Yep. You'd start by dividing by 2. Now, if you're speaking to me of the hocus pocus method that is often taught in high school courses, known as slide to the side, well, that's nice. That's your business, but I refuse to teach it. Because in order to explain it, I would have to make a substitution and go through about a 20-minute discussion. And I refuse to teach methods which aren't grounded directly in applying arithmetic principles. But that's probably not what you're saying. You're probably just saying I should factor the 2 out. Yeah. So if I factor the 2 out, how does that go? I mean, that part was easy. How about the next one, though? What's this? I have to put what? Not 3, but 3 over 2. Right? And how about that 1? One half, right? Well, that stung a little, right? And the thing is, when we're factoring, we're just going to have to leave that 2 sitting out there, minding its own business. You leave it out there. It rides along the rest of this discussion, all right? So it's there. We're not going to mess with it, but we're going to keep writing it because we don't want to change the expression. If we were not factoring, if we were solving this equation, you could divide the equation by 2 and the 2 would disappear. Poof. That's a different situation. We're factoring. The 2 is there. We have to deal with it. It's not a big deal. We just leave it out there. Okay, so I'm going to put some big parentheses here just to keep it out. Now what do? I complete the square on what's in the parentheses. So what's my starting step? I do x plus what squared? These 2 terms here, what I'm trying to get. So my question to you is, what's 1/2? What's 1/2 of 3/2? Because that's what we're supposed to put there, right? 1/2 of 3/2. What's 1/2 of 3/2? Anybody? I got a 3/4. Sounds good. And then 3/4 is great. What's the square of 3/4? It is 9/16. 3/4 times 3/4 is 9/16. So we have to subtract 9/16 here. What I wrote in blue is identically equal to what I underlined in blue in the step above. There's still the 1/2. We still have to add it. So there it is. Now we've got to add fractions. What is minus 9/16 plus 1/2? I'll do that over here. What's minus 9/16 plus 1/2? So you're like, that's minus 9 plus 8 over 16. So you got minus 1 over 16. Lovely. So this is 2 times big parentheses, x plus 3/4, quantity squared, minus 1/16. Everybody follow me? We're just doing arithmetic. There's nothing magical here. There is one magical. What is the one magical step? What is the one non-intuitive step? Is the what? The completing the square step, right? But I hope you're starting to see how to do it. Are you starting to see it? Okay. Now, if you're like, I saw it 10 examples ago, please move on. Well, that's one. I'm glad you're there. That's wonderful. I would like for all of you to be there. So this is 1/4 squared, right? What is the square root of 1/16? Square root of 1/16, right? Is 1 over the square root of 16. Square root of 1 over square root of 16, which is 1 over 4. So I can rewrite 16 as 1/4 squared. And then we have yes?
So wouldn't that be 1 over 2 instead of 1 over 4? Oh, it's just the square root of 16. Okay, never mind.
Okay. I'm kind of tired, so. You could talk me into almost anything at the moment. All right, so this is 2 times x plus 3/4 minus 1, rather plus 1/4 times what? Sorry. Times x plus 3/4 minus 1/4. So again, I'm using the difference of squares. And then you can do the arithmetic. What's 3/4 plus 1/4? So you got yourself x plus 1 times what? X. What's 3/4 minus 1/4? You got yourself 2/4, also known as, more popularly known as 1/2, right? So plus 1/2. If you had a top-notch high school algebra teacher who taught you the sneaky ways that allows everybody to do this, the slide to the side method, you probably would have written your answer by bringing this 2 over here, and the answer would have looked like this: x plus 1 times 2x plus 1. So if you have a good working knowledge of your previous algebra course, you might have derived that with another method. Now, what I wrote in blue, you don't have to do. Hey, that rhymes. This is a perfectly good answer right here. I like it just fine. All right? Are we all understanding the method now?
This is a lot to take in.
Yes, sir.
Can you go over the step, it's like 3 up from the bottom, where it's the negative 1/4 squared, and how you derive the set?
So generically speaking, what we've done before, in the previous example, see, going from here to here, I take whatever I have here and I rewrite it as the square root of it squared. It's the same thing here. I traded my 1/16 for the square root of 1/16 squared, which is,
okay, that
but but the larger point is you're looking to write the number as a square. So sometimes you don't actually have to calculate the square root. You can just see it, right? Sometimes you can just see it. Other questions?
makes sense.
Yeah.
Would you go from the 2 parentheses to your final answer?
Addition. Oh, this one?
No, the one above that.
So from here to here,
Yeah.
difference is,
From the one you're pointing at to the one above.
oh, 3/4 plus 1/4 is 1. And 3/4 minus 1/4 is 2/4, which is a half. So it's just that, yeah. Perfectly reasonable question, but it's just that. Well, I feel like you guys want me to do this with letters. No?
Oh, yeah.
No? Well, that's enough time. Check it out. So ax squared plus bx plus c. Can we factor that? How does it factor? Listen, if for whatever reason it didn't click today, at the start of next class, you can ask me, could you please do another completing the square? And I will happily do it because I love completing the square from the very core of my existence. Like, it's one of my favorite things. I will do another. Let's factor this. If a is not equal to 0, we can factor a out. X squared plus b over a times x plus c over a. Then I will complete the square. A times x plus b over 2a, quantity squared, minus b over 2a, quantity squared. I did what I've always been doing up through all the examples today. I simply completed the square on these two terms, and it gave me those two terms. And of course, I still have the plus c over a, right? Then I go, aha, this is a times x plus b over 2a, quantity squared. And let me just do a little pre-processing here. This is b squared over 4a squared plus c over a, rather minus that plus c over a. So I can rewrite that as like minus, pull a minus out, and that gives me b squared minus 4ac over, 2a quantity squared. That's what this works out to. So I've got a minus parentheses. Well, I could write it this way. It's minus the square root of b squared minus 4ac over 2a. Well, there's not the square. It's not inside the. I can leave the 2a outside the square root here. That squared. That's what the algebra does here. And then the difference of squares does what? So we've got a times what? Times x plus b over 2a plus the square root of b squared minus 4ac divided by 2a, parentheses, x plus b over 2a minus the square root of b squared minus 4ac over 2a, close parentheses. Here are the cases. If b squared minus 4ac is greater than 0, it has distinct real factors. If b squared minus 4ac is equal to 0, it's a repeated factor. If b squared minus 4ac is less than 0, it's irreducible. Because think about it, the thing in the square root, it's either a positive number, so it's like most of the examples we worked today where you're just looking at difference of squares of a polynomial and a real number squared. If it's 0, the whole thing collapses to just x plus b over 2a squared. And if it's negative, well, the thing in the square root gives you an imaginary number, which means we're in a complex factoring situation. Do you guys recognize what this is? No. If you set this equal to 0, we get x equals to minus b plus or minus the square root of b squared minus 4ac all divided by 2a. That's the quadratic formula. When you complete the square, you are building the quadratic formula for your example piece by piece. That's what it is, conceptually. Anyway, oh, I got your quiz for you. So